In this section, we will discuss the different methods for analysis of a heat exchanger. So the topic is heat exchanger analysis. Okay, let us say this is our heat exchanger. Okay, and m dot h and m dot c. M dot h and m dot c is the mass flow rate of hot and cold fluid respectively, and the unit is kg per second. Okay, and the same amount of mass flow rate will exit. This is m dot h, m dot c. Now let us consider or say Tc in and Th in. Th in and Tc in is inlet temperature of hot and cold fluid respectively. Okay, and Th out and Tc out is outlet temperature of hot and cold fluid respectively. Okay, and say CPC and CPH is a specific heat of hot or cold and hot fluid respectively, right? Then we say m dot CPC is equal to CCC, say, and this is nothing but the heat capacity rate of cold fluid, and m dot h CPH is equal to CH, which is heat capacity rate of hot fluid. So if we see here, this is Tc in, Th in, this will be Th out, and its temperature is Tc out. So from the first law of thermodynamics, heat gained by cold fluid is equal to heat lost by hot fluid, right? Which means this will implies Cc Tc out minus Tc in is equal to Ch Th in minus Th out, and this is the amount of heat transfer that is taking place inside the heat exchanger. Let us say this is equation 1. Assumptions in this analysis are: first one is the flow is steady, that means we can write it as a steady state flow. The second assumption is axial conduction is negligible. And the third one is outer tube surface is insulated, or we can say perfectly insulated. There is no heat loss to the surrounding. Okay, so this surface is insulated. Okay, this one and this one also. There are two methods for analyzing. There are two methods for analyzing a heat exchanger. First one is LMTD method, or LMTD stands for logarithmic mean temperature difference. Okay, and this method is used when this method is used when we know the inlet and outlet temperature of fluid. So by this method we can determine the size of heat exchanger. Okay, and the second method is NTU method, and NTU is nothing but number of transfer units. This method is used when we do not know the inlet and outlet temperature of the heat exchanger, but we know the size of heat exchanger. By this method we can calculate the inlet and outlet temperatures of hot and cold fluids. Now we will discuss the LMTD method. Consider a parallel flow heat exchanger. Okay, this is our parallel flow heat exchanger. This is the entry of fluids, and at this point this is the outlet, inlet. Let us say this is TC in, TH in, TH out, TC out. If we draw the temperature variation, what will happen? Since this is a parallel flow heat exchanger, right? Hot fluid will cool down and cold fluid will heat up, right? This is TH in, TC in, TH out, TC out. So consider a small cross section of DS. If we see here, it will be this portion. If we consider this portion, there is in this small cross section DAS, there will be some temperature drop of hot fluid and increase in temperature of cold fluid. Okay, so if we do the energy balance, or if we see the amount of heat transfer from hot fluid to cold fluid, that is del Q dot. This is nothing but del Q dot. This will be equal to heat lost by hot fluid is equal to heat gained by cold fluid, right? From this one we can say dTh is equal to minus Q dot upon CH and dTc is equal to del Q dot upon Cc, or we can write this as dTh minus Tc is equal to minus del Q dot 1 upon Cc plus 1 upon Ch. Let us say this is equation 2. And we know del Q dot can be given as U Th minus Tc dAs. This is coming by the definition of overall heat transfer. So from equation 2, this can be written as right, d Th minus Tc upon Th minus Tc is equal to minus U dAs 1 upon Cc plus 1 upon Ch. If we integrate this equation from inlet to outlet, we will get ln of Th out minus Tc out divided by Th in minus Tc in. This will be equal to minus UAS 1 upon Cc plus 1 upon Ch, right? And from equation 1, we can write Th out, or we can write 1 upon Cc is equal to Tc out minus Tc in divided by Q dot, right? And similarly, we can write 1 by Ch is equal to Th in minus Tc in upon Q dot. These two equations we have written from equation 1, right? So if we substitute this one in the above equation, we will get Q dot is equal to UAS into LMTD, where LMTD is equal to delta T1 minus delta T2 upon ln of delta T1 upon delta T2. So delta T1 is temperature difference between hot and cold fluid at outlet, and delta T2 is temperature difference between hot and cold fluid at exit. Okay, so this equation for LMTD is valid for counterflow heat exchanger also. So this is very important formula. Okay, valid for parallel flow heat exchanger and counter flow heat exchanger both. Okay, so parallel flow heat exchanger delta T1 is equal to Th in minus Tc in, and delta T2 is Th out minus Tc out. And for counterflow heat exchanger, delta T1 is equal to Th in minus Tc out, and delta T is equal to Th out minus Tc in. Let us consider a limiting case where delta T1 is equal to delta T2. So LMTD is equal to limit delta T1 tending to 0 or tending to delta T2 is equal to delta T1 minus delta T2 upon ln of delta T1 upon delta T2, or we can write this as limit delta T1 upon delta T2 tending to 1 is equal to delta T1 upon delta T2 minus 1 upon limit or ln of delta T1 upon delta T2. By L'Hospital rule, LMTD will come out to be delta T1 is equal to delta T2. Important.